Go ahead.
Yes, I have a question, sir.
Okay.
Okay, I want to this week. Can you? Is it possible for? Can we? Is it can we use for image data? Like if we want to use for classification or prediction artificial neural network. Can we use for that, or is it only for numeric data?
No, no. You can use it. You can use Weka for anything. There's even deep learning there. So, sorry, I'll mute all because of
Okay.
the somebody is talking unknowingly in the background. Okay. So who asked the question? Is that Mr. Kiola?
I just want to ask my question, sir. Good morning, Prof.
Okay, just hold on. Let me answer the first question. Just hold on. Thank you. For the first question, the question was that can Weka work for image processing? Yes, it can work for image processing. Yeah, so the same procedure taken. Yeah, you have to load in your data. So, and then of course you have to extract your features. Your feature must be extracted. However, if you want a system that can extract feature for you from image automatically without making effort, because you have to, first of all, the standard machine learning model requires you to extract your feature using image processing software, using all this bitmap and pixels. They will remove it. It will become like numbers that you can put in Excel file. You see, you can put in Excel file. So you can use, some people do it manually, some people use some image processing software to extract the features. And then once it becomes like the number the one we just modeled today, it will be in a CSV file. You upload it, you can use k-nearest neighbor or any other machine learning algorithm to do it. That is one. However, if you don't have the features already extracted from the images, then you use the deep learning part of the machine learning. It's also in Weka. So you have deep learning also in Weka. So deep learning, the unique capability of deep learning is instead of extracting feature using image processing software first and put it in in a CSV file or Excel file in a format the machine learning algorithm can use, deep learning has the capability to automatically extract the feature. Just give it the feature, it will extract it by itself. And that is the big game-changing capability that deep learning brought on the table. And that's why real-time processing of images became possible, like in autonomously driven car, the car without driver. So it needs a lot of videos, images to be taken. And at real time, the deep learning component, we extract the feature and determine is the image, is the human being that is crossing so that the car can stop? Is the car in front closer than necessary? And all those kind of decisions we need to do. If without deep learning, such capability may not be possible. Also, you want to extract my voice as I'm talking, you want to convert it to other languages in real time. There's no time to ask somebody to help you extract the feature and convert it to number, then you can then upload it to the machine learning model. No. So we need a system that can automatically pick my voice, process it, extract the features, and then convert it to another language so that somebody can be hearing me in his own language as I'm talking. That is made possible by the capacity and capability of deep learning. So for image processing, we recommend deep learning. Although at the long run, once you extract feature using deep learning, it's also good to let those features be passed to classical machine learning algorithms. Because sometimes we've seen cases whereby the deep learning that extracted the feature was able to get like 80% accuracy in the final modeling. However, once we brought the feature extracted by deep learning and we pass it to another machine learning, the standard machine learning like k-nearest neighbor, they perform better with like 99% accuracy or performance measure. So that's why sometimes we encourage a mix of deep learning, especially to use deep learning to extract the feature, while we use the standard machine learning and the deep learning to do the final analysis and prediction so that we can compare them. And we have seen a lot of improvement when we let them work together as a team. A team is always better than an individual. So I hope I answered that question. Mr. Akinola Ebitiga, am I right? Am I correct with your name?
Yes, sir.
You have the
A
floor.
bit.
You have
Yes,
the
sir. Good morning, Prof. Thank you for the lecture, sir.
You're welcome.
And God continue to help you, sir. And sir, I want to get a clarification between under hyperparameter optimization, we have the number of K to be considered. Is that also related to the epoch? Is the number of K to be considered the same thing as the epoch to be run while carrying out the data processing?
Okay.
Is it the same thing, sir? Or what is epoch?
Okay, thank you very much. Thank you for the question. You see, each algorithm has its own hyperparameter. See, when you talk of epoch, you'll be talking of epoch when you're talking of machine learning, artificial neural network, okay? That is how many number of runs we're going to make before we can take a decision that this is enough. Because there's a threshold of error after which you have to stop. This is obtainable in case of neural network. And neural network is the forerunner to all this machine learning training and the like. However, the algorithm we just discussed, K-nearest neighbor, it doesn't build any model, actually. It only stores the training set. And when the new sample comes, it compares it with the training set that is stored in the memory, and then try to see which one is closer together. So the K we are setting is, should we use, because the idea of K-nearest neighbor is, show me your friend, I will tell you the kind of person you are. For example, if it is classification problem, I want to determine if somebody is having diabetes or not, or if somebody is good or not good. Let's look at this example. I will look at all his neighbor. We have data set. Compare with 3 of his neighbor. So you first of all compare with all the data that is available. And then you look at the 3 that is most closest to this guy. If out of these 3 people, 2 of them are bad guys, and 1 of them is good, then we declare that that guy is a bad person. That is the K we are looking for. How many neighbors should we use to decide? You see, 1 neighbor, or 3 neighbors, or 4 neighbors. That is what we were optimizing. When we keep changing K is 1, K is 2, K is 4. Until we got to 7 or 6, we noticed that the result was getting bad again. So we moved back to the one that gave us the best value. So K-nearest neighbor, it doesn't need the number of epochs. It's not applicable in its own case. In its own case, the hyperparameters include K, the number of K, which is number of neighbors to be used for decision making, and 2, the distance measure, which is Euclidean distance, Manhattan distance. You keep checking them. These are the 2 hyperparameter values that we need for the case of K-nearest neighbor. And how do you know that? If you go to K-nearest neighbor here, you see, Weka will tell you, this is K-nearest neighbor, this lazy classifier. Let me see, I'm choosing K-nearest neighbor, IBK. It will show you the hyperparameters. It's only 1, K is 1. And then it's changing to Euclidean distance. These are the 2 hyperparameters. There are many parameters here, but the hyper, they are the ones that affect the algorithm. Like, for example, number of decimal places. This has nothing to do with the algorithm. It's saying how many decimal places you want your result to be shown. 2, decimal place 3, it has nothing to do with the algorithm performance. However, number of K and the distance measure, they are very important in the performance of the algorithm. And those are the ones we call the hyperparameters. And that's why it is stated here. K is equal to 1. That is the default value. And the distance measure is Euclidean distance. And that's why we kept changing them as the case may be. For this algorithm, it's only K and the number of and the distance measure. For support vector machine, we have others. For neural network, which we are very much conversant with, we go here, you can see shoes, you're going to see in under function, the multilayer perceptron. This is multilayer perceptron. That is the neural network. You can see it has a lot of hyperparameters. You can see this is 0.3, M is this, number of hidden neuron. See, so it has a lot of hyperparameter. So we have to identify the hyperparameters, the number of epochs like you mentioned, and then depending on the implementation that you are using. So this is why neural network has more hyperparameter compared to K-nearest neighbor. That's why we call K-nearest neighbor very simple algorithm. we start with it first. In fact, there's another one that is more simpler, Bayes net or Nave Bayes. It's also here. Nave Bayes. This is Nave Bayes. Sorry, Nave Bayes is here. Yeah, Bayes. You see, we code to Nave Bayes. Nave Bayes. This is Nave Bayes here. Number 2 is gray out because Nave Bayes does not work for regression problem. You cannot use it to predict numbers. And we are predicting number presently. That is why it is gray out. If you are dealing with classification problem, you want to say, is it correct? Yes or no? It will not gray out. We select Nave Bayes. One of the advantages of Nave Bayes is it has no hyperparameter, nothing to optimize. Once you run it, it's either it is correct, it can undo it, or it cannot undo it. And it's very powerful when you are working with text classification problems. So it has no hyperparameter. So it depends on the algorithm. The algorithm has a set of hyperparameter that has been defined before they can work better. I hope that answers your question, Mr. Akinola.
Yes, sir. Thank you, sir. Thank you, Prof. Yes, sir.
Thank you very much. So last but not the least question here is from Mr. Biliamin Suleiman. He said, thank you, sir. How do we determine the satisfying performance of a model? Is there any standard? Yes, a very, very wonderful question. It depends. If you are working, you are trying to solve a problem that someone already solved before, then you go to literature. Of course, this is the first place to do. You go to literature, search for what they have done. Someone already worked on the same data like you, like the data you want to use. Someone already used it before, and he achieved like 70% accuracy. And root mean square errors also something not yet acceptable. Then you know there is need for improvement. That can be your main contribution. You want to improve what they have done. From 70, you are targeting like 90. If you can even push it from 70 to 80, that's a good development, especially if it is a very important topic. And you're able to improve it from 70% to 80%. You have made a contribution. However, in medical, we want to push it to 99, even possible 100% or 95. So however, if you are the first one to solve a problem, then you are the one to determine where to stop. If you get it at 70 for the first time, no one has ever worked there, that would be something to celebrate. You understand the terrain. For example, there was someone was working in the area of membrane technology in chemical engineering. You see, the data was brought in and they will look at the data. We were just still working. We wanted to do more. We achieved 70, maybe 75% accuracy. To me, we are not done with hyperparameter optimization. We still need to change the algorithm and check other algorithms. But when they heard that we already achieved 75%, the man screamed and said, no need. We never had 40% before when we were using statistical methods and SPSS and the likes. Said 73 is super. He asked us to stop the modeling. And it was presented in one of their topmost journals in that field. And they appreciated it and accepted it within a few weeks. So you can see 75 to medical in some area is not acceptable. But to those people, this is more than what we have in literature. In literature, we had 35%, 40%. Now you have taken it to 75. That is something we can celebrate. However, if the people have been getting 90% in your area, then you have to head to be able to get something more than what they are getting. So that is why, how do we know or determine the satisfying performance of a model? Is there any standard? You have to see. If you are the first one to use it, then you will determine what satisfies you at the beginning. If it is a new area, 80% for a start is not bad, provided you are going to get a journal that will recognize and appreciate it. However, we always aim towards the 90% range because you are trying to let people trust your prediction. Like if you go to laboratory, because what we are saying, instead of going to laboratory and spend 2 weeks, we can use predictive solution in machine learning to estimate what you are going to get in lab after 3 weeks. Why wasting your time? For that professor to trust us, we need to have acceptable level of error, minimum number of error that may come. Instead of getting 0.2 in his result, he's getting 0.25 or 0.21, which is acceptable. So This is, I believe, how we can answer that question, how it is clear. How can it be related to education? Yeah, a lot of, thank you very much for that questioner. Relating to education is huge. Hopefully, we're going to be having series also on education soon. At the goal, we want to be able to monitor the academic performance of our students. And then we want to see how can we improve the teaching methodology of some selected, like STEM subjects that are getting popularity these days, sciences and some other subject we are interested in. At the beginning of a school system, we want to be able to have an idea of what the performance of those students may be. Usually, we wait for students to have problem, drop out. Why do we allow students to drop out? In a system that is data-driven decision-making process, we can have an idea of, because we have huge data of students who drop out in the past. Why did they drop out? Now we have new students coming in. Can we run a machine learning based model that can tell us, because there are some characteristics in the new student that shows that people who suffer from this kind of characteristic, they drop out, so that we can have an interventionist system, approach them, proactively detect those students at risk of dropping out, and then we can have special guidance and counseling for them to prevent them from actually dropping out. So machine learning is not a doomsday prediction system. We want to have an idea of something that may go wrong, and we then try to see how can we prevent it from actually going on. To get to a class, you run the model based on previous student data. We run a model for my course. So I identify that 10 out of 50 students in my class may fail that course. We invite them and sit them down. Why are they going to fail? We're going to discuss it later. Diagnostic analytic. We can try to find out why will they fail. It to try to identify some of the characteristics that may possibly make them to fail. Then we can work on those weaknesses of those students, like giving them extramural classes. Some of them have not paid their school fees. Some of them are having some challenges from home. We send them to counseling center so that together we can prevent our students from failing. We can prevent our students from dropping out. And like I said, hopefully we'll put it on our agenda. AI in education, maybe it's one of the areas we are going to explore in our future encounter. Once again, thank you very much all for listening. I believe we surpassed our time. It's already 5 minutes past the time. Thank you very much all for listening, and I wish you all the best.